Okay, the third talk today is by Mitchell Riley, who's at Wesleyan University, and he will be talking about linear homotopy type theory. Please go ahead.
Okay, thank you to the organizers. Today, I'm going to be giving a bit of a follow-up talk to one that I gave at the HoTT conference a little while ago, which was talking about this modality, which we had added to type theory, to try and talk about some stable homotopy theory inside type theory. And this talk will be on a further extension of that type theory, which adds some linear type formers to homotopy type theory. So I'll just try and remind us of what the setting is that we're interested in. Our intended model is space parameterized families of spectra, which form an infinity one topos. But more generally, this type theory should have models in X parameterized families of C, where X is some infinity topos, C is a symmetric monoidal closed infinity category with a zero object. We need that condition. And so every object in this setting sort of has a nonlinear aspect, which is the indexing object X, and a linear aspect, which is all of the fibers, which have the symmetric monoidal structure. Okay. And so I'll use the same picture that I always use in these talks, which is, I think of these objects as looking like this, where in the base we've got some space, and then over every point we have a spectrum, and these spectra vary continuously as we move around the space. And so there are some basic constructions which we can do with these objects. And the first one is, if we have one of these guys, we can just replace all of the fibers with the zero object. And so this is this operation we called natural, which was the subject of the previous talk. But something else we can do is we could look at the fiber-wise monoidal product. Oh, sorry, the external monoidal product of two of these objects. So if we've got two of them, then when we take their external monoidal product in the base, we take the product of the two inputs. And then in the fiber over every point in the product, we take the monoidal product of the two corresponding fibers of the inputs. Okay, so if you're interested in the first thing, we have this note on the archive with Eric Finster, which shows that we can do some fairly interesting things just with this first operation. But now we're going to discuss the tensor product. And there are a couple more linear type formers which our theory has. We have the unit of this tensor product and also a right adjoint Hom, but we'll see if we have time to get to that at the end. Okay, so the reason we might be interested in these is that if we have these type formers built in, we can give a pretty slick definition of homology and cohomology. So just combining all these things together, homology corresponds to a use of the tensor product, and cohomology to a use of the Hom. But I'm not going to discuss this either in this talk. Okay, so these new type formers that we're adding, we want the result of using them to give us just ordinary types in the type theory. And so this rules out a lot of the previous work on dependent type theory and linearity. For example, we can't use index type theories where there's a separation between the linear types and the nonlinear types, because then we can't use the ordinary constructions in HoTT on the linear things. And it doesn't seem possible to use quantitative type theories for this either, because the quantity annotations on the variables get in the way of the ordinary HoTT constructions, which we might like to do. So we need a new strategy here. Okay, so let's go to the tensor. So let's jump way ahead and pretend that we already have a tensor type former, and try and write down the proof of symmetry that we would want to have for this. So, to define this equivalence, we need to give, first of all, just an ordinary function from left to right. So to define the function from left to right, suppose we have a term of A tensor B, then there should be some kind of tensor induction, which lets us assume that the term of the tensor that we're given is equal to the tensor of two things. So X is the term of A and Y is the term of B. And then if this is the case, then we should be able to form Y tensor X the other way around. So this should be the definition we can give for the symmetry function. And then to prove that this is actually an equivalence, we need to show that if we compose it with itself, we get the identity. And so for this, we should just use tensor induction again on this P. And then on the left-hand side, we've applied symmetry twice to X tensor Y. So it gets flipped back. And then we just have reflexivity for the path. Okay, so this is where we want to end up. But we need to somehow restrict variable usage. So tensor in general is not supposed to have a diagonal map like this. So we shouldn't be able to assume we have a term X of A and then form X tensor X. So variable use needs to be restricted somehow. And so the solution that we're using for this is we're going to label every variable in our theory with what we're calling a color. And the relationships between the colors of all the variables are going to be collected in a piece of the context we're calling a palette. And so the palette is going to control how the variables of each color are allowed to be used. Okay, so the grammar of palettes looks like this. We have an empty palette. If we've got two palettes, we can tensor them together. If we've got two palettes, we can combine them with a comma, and this should correspond to just ordinary, this should correspond to taking the Cartesian product of the two palettes. We have a single label. And finally here, we have a label which is giving a name for a sub-palette. So typical palettes might look like this. Over here, we've got purple, which is labeling the palette red tensor blue. So we might read this as like purple splits into red tensor blue. And then we can, of course, nest these things however we like. And so we have the palette from before. We might take purple tensor Y and then give the resulting palette a label for brown. So brown splits into purple and yellow, purple splits into red and blue. And then we could also use this comma over here. We might say that purple splits into red tensor blue, but it also separately splits into red prime tensor blue prime. And so in general, combining these two binary operations, our palettes end up having a tree structure, which is quite similar to bunched logic and bunched type theories, which have been studied in the past. But here, the colors don't have a type or anything like that. They're just labels. Okay. So now how does this affect the variables? Well, when we're working in this theory, we need to keep track of what the current top color is at the place that we're working. So suppose our palette is purple splits into red tensor blue, and we have the following variables. Then if we're trying to form a term in this context, the top color here is purple. And so the only variable that we can use immediately in this context is Z, right? If we were able to use X or Y here, that would correspond to a projection from one of the sides of the tensor, which is something we're not supposed to be able to do. So all of the ordinary type formers of HoTT, if we're working in a context with top color purple, all of the variables which are bound in the all the ordinary term formers will also be purple. So the things that we have so far don't change the color that we're working in. But then the rules for the tensor type are what will interact with the palette and give us access to these other variables if they're currently unavailable. Okay, so here are the rules for tensor. Take one. So suppose we're working in a palette with top color purple. Then if we've got closed types A and B, then there is a type A tensor B. And here I've got closed asterisks because we can relax this. They don't quite have to be closed. If you happen to have seen the last talk, the restriction that we need here is that we need these two types to be dull, which is a syntactic restriction on the way variables can be used in them. If you've seen Mike Schulman's cohesive type theory, it's similar to being crisp. So you can, if you've seen that, you should think of these as crisp types. Right. Now, to introduce a term of this type, if a top color of our palette splits into two colors, we have a term of the with the color on the left and a term of the color on the right, then we can tensor them together and get a term of the tensor product, where we've annotated the tensor with the colors that we're using. And to eliminate a term of tensor type, we have this tensor induction principle, which we were hoping for earlier on. Whenever we have a term of tensor type, we can assume it's of this form for some new variables, x and y, and then use that to prove a term C. And then we have sort of the expected computation rule, which is if the term that you're doing induction of really is of the form A tensor B, then the induction reduces and you just substitute in the data of the thing you're doing induction on into C. Okay. So now let's go back to symmetry. First of all, can we get a function from A tensor B to B tensor A? Well, sure, we can start by assuming we have a term of this side, and then tensor induction gives us a variables of the types on either side. And now to conclude B tensor A, we need to form a purple term of B tensor A. And so we want to split purple into blue and red so that we can form the tensor the other way around. The problem here is that in the palette, we don't literally have purple splits into blue tensor red because we have the induction has given it to us the other way around. So we need to build in the symmetric monodal structure into the palettes somehow. And so here's how we do it. We need another judgment for saying when our palette linearly splits into two monoidally combined pieces. And so here, the judgment looks like this. We've got the two pieces just divided by the bar. And in general, the pieces that the palette splits into might not be just individual color labels anymore. So just indicated that with little arrows. And so I won't give the formal rules for this split judgment, but we will be allowed to conclude, for example, that in the palette, purple splits into red tensor blue. We have a split with the colors on opposite sides. This judgment also builds in associativity. So in the palette from here, before we have this triple tensor, we want to assign red to one side and blue tensor yellow to the other side. So drop in these other labels. And this judgment is also where we build in Cartesian weakening of the palette. So in this palette, where purple splits into two independent tensors, we're allowed to forget one of them and just declare that purple splits into the red prime and the blue prime. Okay, so just inserting that into our rules, it just means that in the introduction rule, we're allowed to use any palette split. It doesn't have to be something that appears verbatim in the palette to form the two sides of the tensor. Then the elimination is the same, and the computation rule, the only difference is now we might end up substituting a list of colors for a single color, but that works out as well. Okay. So now, as another example of this type former, this tensor is a positive type, and so we should be able to prove a propositional uniqueness principle from its computation rule. And indeed we can in the expected way, which is that if we have any type family over the tensor of tensor A of A and B, then if we do induction on a term of the tensor and then immediately use the two pieces combined by a tensor again, we may as well have not done the induction at all. And so, I mean, the proof of this is we're trying to prove this, and so we do tensor induction on P, which gives us that it's equal to x prime and y prime, and then both sides reduce to f applied to x prime tensor y prime. And the reason I point this out is that this is the kind of thing that we can't do in other linear dependent type theories. For a couple of reasons. One of them is that, first of all, we have a type family over a linear, over a use of the linear type formers, which is the first notable thing. And the other one is that this might end up giving us paths in a tensor. So, for example, if you imagine this f is just the identity function, then the path with which this is constructing is a path in a tensor B. And so I don't believe identity types of linear types is something that could be done in other type theories. Okay. So I'll just briefly say something about how dependency works with tensor. So just a review from the way this modality works, the natural modality works. Any assumption, we share with that type theory the fact that any assumption that we have can be used in this special way, which we've been calling marked. So whenever we have a variable x, we can choose to use it as sort of x underline. And semantically, what this corresponds to is sort of taking the round trip of A, the type A, through that natural modality, which kills all of the linear information. So we're mapping it through the operation which sends every fiber to the zero object. So it's ignoring the linear aspect of the type A. And then there's the syntactic addition on terms and types, which is that we say a term or type is dull if all of the free variables that occur in it are marked. They use marked usage. And then, sort of as I mentioned before, if we have A and B, which are dull types, then we're allowed to form A tensor B. And in fact, we can be a little bit more permissive than this. Similar to the Cartesian product, we're allowed to have the type B depend on a term of type A, but again, only in a dull way. So if A is a dull type and B is a dull type, assuming a term of A, then we have this kind of dependent tensor. Okay, and just for example, just like we have associativity of the ordinary Cartesian product, we also have dependent associativity of the tensor. And the only difference is that down here we don't have projections, so we have to manually pull apart the thing on the left to use it in the dependent type C. Okay. All right, I'll say something about Hom, which is, I won't give the formal rules for it, but here's how you might invent them. Which is, first of all, we can just look at this analogy between the rules for the Cartesian product and the rules for the tensor product. Sort of in linear logic, we have rules like this. And so we can, the first step is just to assign terms to these things. So over here we have the ordinary dependent functions. Over here, it's just the same thing. We have a variable now which is tensored with the rest of the context, and a kind of Hom introduction lets us abstract that. And then the only thing that's left is to write this using our palette notation, which here on the left, as we said, all of the ordinary dependent types just bind variables or whatever the current top color happens to be. And on the right, what happens is the original context that we have gets tensored with the new variable, right? It's tensored with a new color, and the new variable is given this new color, right? So something that's interesting is that going under one of these Hom binders, B here loses immediate access to all of the variables in gamma, right? Because all of the things in gamma are red or some subcolor of red, and the new top color in here is purple. And so the only way to get access to these variables again is to continue to use the linear type formers like tensor intro, or to unlock the variables again. And so an interesting fact about this Hom type is, well, first of all, we can define a map like this that goes from any equality between two Homs to kind of a pointwise equality between them. Where here, by pointwise, I mean sort of in the Hom sense. And we might ask that this map here be an equivalence for any two Homs. And it's a surprising fact, or it was surprising to me, that univalence implies Hom extensionality, just like univalence implies function extensionality. And the same proof that you use for functions also works for Homs. All you have to do is go through the proof and check carefully in every place that all of the linearity conditions are satisfied. And it feels a little like a miracle to me that it all works out and everything is used linearly. Okay. All right, so what is this good for? Well, first of all, we should be able to formalize some more arguments in synthetic homotopy theory using this type theory. So as an example, Urs Schreiber has a lot of notes on homotopy type theory and cohesive homotopy type theory. And in some of them, he hypothesizes that there should be some notion of linear homotopy type theory, and then gives a bunch of results that ought to be provable in it. And I believe that we can now formalize all of those in this type theory. I think we can do all of the things he gives in this this section of his notes. And another intriguing possibility is there are some people who have worked on dependent type theories to be used as like a specification language for quantum circuits. And the intended models that they are using are very similar to this kind of linear objects parameterized by nonlinear objects setting that we are in. And so I believe it's possible to adapt our type theory to be used in that setting as well. But maybe more important than those applications is that in recent years, there have been a lot of new modal extensions of HoTT. And here I've listed some of them. And they're all sort of added manually. And you have to reprove all of the meta-theoretic properties of them sort of from scratch in each new setting. And so there have been some efforts to kind of do this systematically. The first one is this multimodal type theory framework, which was mentioned in the last talk as well, which can handle a lot of these settings. So certain kinds of adjoint modalities, it can do ordinary dependent types, but it can't do substructural types like linear types. And another effort is the one started by Dan Liccardo and Mike Schulman, which I've been helping with, which can handle any kind of modality, but so far can only satisfyingly do non-dependent types, but it can do linear types. And so this linear homotopy type theory that I've presented in this talk doesn't fit into either of these frameworks. And so I believe would be a good test case for whether extensions of these possibly to meet in the middle are sort of on the right track. Okay, and that's the end. Thank you very much.
Okay, thanks a lot, Mitchell. Now we will thank the speaker silently again. And we have time for questions. Is there any kind of proof assistant that you can use for this?
I don't think there's one off the shelf that you could use. I have been writing a sort of custom one for myself, but it's not particularly usable at the moment.
Okay.
And that has some sort of interesting. There's some interesting things you have to do there to make this palette stuff behave nicely with like the usual like normalization by evaluation tricks.
Okay. Anybody else?
I have a question. So you say linear HoTT doesn't currently fit into any of these frameworks. Is this because it's dependent, or is even the non-dependent version of it something that doesn't fit into the vibrational framework?
So the non-dependent version of it should fit into the vibrational framework fine, but that's not too exciting, because the non-dependent version of this theory is quite a lot like just the bunched type theories that I mentioned earlier on. Really, the only difference between the non-dependent version of this and the bunch type theories is this modality, which I think is new. The natural modality, I mean.
Sorry, I just lost my mouse for a second. All right, I guess we'll wrap it up there. I'll turn off the recording.